Welcome to queenon7.com. Please like and share my videos. Today we're going to learn on the second part of the transition metals. We will look at the shape of the transition metals. So we will start it with the octahedral. Now the octahedral, you probably heard of octahedral when you have done the topic of the angles in the AS level. So today we're going to look at any molecule. For example, if I put copper, I'm not going to put a charge there now. If it has 6 bonds with other atoms, it is an octahedral structure. Now in transition metal complex, basically these are the coordinate covalent bonds. Now if you have OH negative ion, the overall charge will be -4. 6 for the OH ion and the metal ion carry on +2, so altogether -4. Now based on that, the structure will be straightforward. It's an octahedral structure, and we will look at the tetrahedral next. Now if you again have copper and you have chloride. Now copper is 2+, so the overall charge is going to be -2. Copper is +2, each chloride is -1, so altogether it's -2 charge on the complex. Coordination number here is 4, here you have 6. Now this is just like CH4. The moment I'm going to use, for example, if I change those two chloride with NH3, and you will have NH3, and you have Cl and Cl, and that will actually have 0 charge because copper is 2+, if it is, and chloride is -2. Now based on that, why do you think that copper cannot accommodate 6 of the groups or ions or atoms around it? If you look at it, the problem is actually the size of the atom or ion or the molecule which is actually used as a ligand. In this case, the chloride itself cannot be actually occupied 6 places as octahedral. Chloride has an atomic number of 17 electron, big molecule, as compared to oxygen which has only 8. So oxygen is smaller molecule. Because of the size of the ligand, it can only occupy 4 different positions, and it's not going to go under octahedral. Now same goes for this one. Even you have NH3, NH3 can be attached on 6 sides and can make an octahedral structure just like OH, but because the 2 of them are chlorine or chloride ion, they are actually going to oppose the further substitution or further addition of the other ligands on the copper ion. Linear we have done in the previous video, where we have done NH3, and then you have NH3 is +1 ion. The coordination number is 2, but the overall charge is +1, and here is +0. Now we're going to look at the cis and trans isomerism. Now if you have, for example, if you have nickel, and which is attached with Cl and Cl on this side, and you have NH3, NH3, because they both are on the same side of the central metal complex, central metal atom, sorry, the overall charge is obviously 0 because of the charge on the nickel. You can have another one which is actually in the trans position for the molecule you have. So chloride is now in the trans position. Here you have on the same side. This one is actually a cis complex, and this is actually a trans complex. Now cis and trans isomerism, you probably read that in the alkanes chapter, alkane and alkenes chapter, when you looked at the alkenes where carbon is attached with the 2 different atoms or groups, and then you actually compare them with either with the priority or if they are same, and you predict the position, either they are on the same side or on the opposite side. Now these have got vast application in industry. We're just going to look at the next part of the isomerism, which is actually the optical isomerism. Now if you have a bi-dented ligand, a lot of people actually struggle when you draw the shape of the bi-dented ligand around the nickel or copper ion. If you have, for example, nickel and you have a bi-dented ligand. If I draw that NH2 CH2 CH2, and you have NH2 there. Now this is actually a bi-dented ligand. Both will deliver the 2 electrons pair to nickel. So to draw that, I will request you to look at the video very carefully. How you're going to draw it is actually a kind of octahedral structure. So you draw a normal octahedral structure like that. Now on each of them you will write down the part of that group which is going to donate the electron pair. So you will write down NH2, 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 NH2. Now 2 NH2 are coming from one molecule, so basically these two are actually connected. So based on that, if these are two connected, so we can actually join them together. But my request is just put CH2 there, slightly lower than this one, and another CH2 slightly above than the angle of this NH2. Now you can actually put the lines there to show that this is actually a one molecule. After that, you have 2 NH2 there. Again, it's going to be CH2 there and then CH2 there. And you're going to draw a line there, line there, line there, and you have 2 coordinate covalent bond. Same goes for this one. So you have CH2 there and then you have CH2 there. So you will combine these and show the coordinate covalent bond and the bond between them. Now this is actually a bi-dented ligand. So you can see that the coordination number will be 6. A lot of people think that the coordination number means how many ligands are going to make coordinate covalent bond. The basic definition is how many coordinate covalent bond you're going to make. 1, 2, 3, 4, 5, and 6. Even though you have only 3 ligands around the central metal atom, they're still gonna make the 6 coordinate covalent bond. Hence the coordination number will be 6. The overall charge, obviously this is actually a neutral molecule, doesn't carry any negative or positive charge. In this case, nickel is actually in +2 state, the overall charge will be +2. Now what's going to happen is, if you have nickel again, this molecule can be actually present in a different sort of arrangement. You can draw the same again like you did before, and now in this case you're going to draw NH2 there again. This time, this part is going to be written on this side. So if you do that, you put CH2 and then you have CH2 there, there. Then you have CH2, CH2 there. And then you have CH2, CH2, CH2 there, and coordinate covalent bond. Now, whenever, so I can teach you the optical isomerism as well. So if this is the molecule, if the mirror image of this molecule is not superimposable onto its mirror image, then they are actually showing optical activity. That means when you're going to put into the polarimeter, it is going to bend the polarized light in opposite directions, whether positive or negative. Now if you look at this one, if this is the molecule and this is the mirror, and the molecule will look like this in the mirror, and I put this molecule right on top of it, if the molecule doesn't have the non-superimposable image on its mirror image, then that means it will show an optical isomerism, because these two groups are actually in the opposite direction. So it's not superimposable like this. That is superimposable. So it is not superimposable. That is called cane in gold isomerism. Now, based on that, this complex obviously will have the same structure but the different arrangement of atoms around the center metal atom. They can show optical activity. So the optical activity can be shown by the transition metal complex. There are some other as well, when you can look at that octahedral structure which show some sort of optical activity as well. But for this now, at the moment, this is what it is for the bi-dented ligand. Thank you very much. Keep your comments, write your comments in the video so I can actually upload more videos. Thank you very much. Bye.